So good morning students, welcome to the second lecture in current electricity. Okay, we already had one lecture on current electricity. We have stopped at current density, so today we'll be starting from there. Okay, so welcome to our channel. What exactly you want to know about me, you'll get in the description box, right? So current density. So in the last class, towards the end, we have defined current density. If we're using a conductor, then through this conductor, a uniform current is I, and suppose this particular conductor is having uniform cross-sectional area, then how we have defined current density as current per unit area. Okay, so this is this particular relation is correct in that situation when through the cross section current is uniform. For example, there is a conductor. If we consider any point here, one point here, okay, the other point here, another point here, another point here, another point here, if current at each and every point of this cross section is same, current at each and every point of this cross section is same, then the current density will be defined as current per unit area. For example, exactly current density is basically defined at a point. They say this is a current carrying conductor. I have considered a small area of this cross section, small area of this cross section, suppose dA. The total current flowing in the circuit is I. Suppose through this particular cross section current flowing is di. Current flowing is what? Di. Then current density will be defined as current divided by area. Okay, so this is a vector quantity. Current is a scalar quantity, but current density is a vector quantity, and the direction of current density is same as the direction of current. Electric current, it has direction, but it does not behave as vector because it does not obey vector law of addition. Current density is a vector quantity. Okay, and the direction of current density is in the direction of current, which is basically going to be normal to the cross sectional area. Clear? Okay. Now if the cross sectional area is not perpendicular to current, क्या करोगे? Right, the cross sectional area is given like this. This is the area, so area vector will become like this. Current is flowing like this. This is the direction of current. Current is going along this direction. Area vector is along these directions. अब current density कैसे define करोगे? How will you define current density now? How you will define current density now? तो इसमें क्या करेंगे हम? We'll consider a small area. Okay, dA. The direction of this area vector is like this, normal to. Okay, any area, magnitude is A, direction of this area is what? Area is a vector quantity. Always normal to the area. Always normal to the area. So this n cap is the direction of area vector. This n cap is the direction of the area vector. We are considering an elementary area dA. Through this elementary area, suppose current flowing is di in these directions. So how we will define current density now? Here current density Z will be defined as, instead of we have to consider the cross-sectional area, not making an angle with the current, but in the direction of current. So for that what we'll do? You see, di is in this direction and area considered is along that direction, dA. So what we will be doing, we will consider the component of dA which is perpendicular to the direction of current. So if this is theta, then this is also theta. if we call this area, if we consider this particular area is DA, then component of this DA along this direction means from here at an angle theta, we have a particular length on this side. We have to find a component of this length along this side. If this is DA, this is theta, then from this triangle, this is perpendicular, base, this is base, and this is hypotenuse. Hypotenuse is DA, base will become how much? DA cos theta. So in the situation, we cannot consider this entire area. When we will integrate DA, we will get entire area, but we will not be considering this area. We will consider area perpendicular to the direction of current. Okay, so from here to here, this angle is theta, same angle. So now current will be defined as what? J will be defined as what? DI through these portions, DI, and this area DA, but we will not be considering DA. Instead of DA, what will be considered? DA cos theta. Clear? Or from here you can see DI, you get an important relation from here. DI is equal to J DA cos theta. J DA cos theta. Or you can write DI, this is a scalar, this is also vector, this is also vector, this is the angle between them. So we can write J bar dot DA bar. J bar dot DA bar. Okay, this way you can find it. Current from, if you want to find total current, then you have to integrate it. That's all. Okay, but here let me remind you one thing. We are taking the component of DA normal to the current. But if you take the component of current, if you take the component, current is along this direction. If you take the component of current, because see, when you say work done, let us go to the definition of work done. In class 11, we have learned it, work done. What is work done? I have applied a force along this direction. Body got displaced along that direction. What a vector quantity? Angle is what? Theta. So how do we take work? We take work force into displacement in the direction of force. We consider the component of displacement in the direction of force. How much? If this is R, if there is R, this component will become how much? R cos theta. So R cos theta into force. That is what we get. Work done. Or we can call it like this also. If this is the displacement, this is the force, then what we can do? We can consider a component of force in the direction of displacement. Both way, your definition will remain the same. But in this situation, current is not a vector quantity. Okay, current is a scalar quantity, right? So we'll be considering, it's not like that we can do it both way. Like once we have considered a component of area in the direction of current, normal to the direction of current, and second time we have considered a component of current which is normal to the area, right? So like DA cos theta, that will not be applicable here, right? For example, once I have taken R cos theta, in the second situation I have taken F cos theta. Same thing will not be applicable here. No sir, once we have taken DA cos theta, component of area, this is the area, we have considered a component of area normal to the current. This is DA and this is what? DA cos theta. Sir, what if this is the current? Current is like this angle is theta, okay, the area is DA only. Sir, can't we consider the component of current normal to the area? Okay, this will not be applicable here. Okay, here is current is a scalar quantity. We do not go for resolution of current like this. But when we consider ideal current, there we resolve. That is a different situation. Okay, so here you remember we'll take the component of area normal to the. We'll take the component of area normal to the current. This is current density. Right. Let us try to find out current density. Let us consider a rectangular body. Let us consider a rectangular body. Like this. Let us consider a rectangular body. Length is L, breadth is B, and height is suppose H. This is a cuboid. Okay. Through this cuboid, at this particular point, along its length, current, how much current is flowing? I current is flowing. We have to find current density in these situations. This is cuboid. Suppose we are connecting to a battery, something like this, as a result of which current is flowing. So we have to find current density यहाँ पर. कैसे निकालोगे current density? Very simple. Sir, current density will assume the current to be uniform. Okay. Let me remind you one thing. Current density uniform, current density uniform. Let me remind you one thing. For example, this is a cylindrical conductor, and through this cylindrical conductor, current is flowing. Okay. It is not necessary that current at each and every point will become uniform. There will be uniform distribution of current across the cross section. It is not necessary. Maybe it may not be. It's not in every time. For example, you are using alternating current with high frequency. What you are using? Alternating current with high frequency. Then what will happen? Then the current will reside on the surface. We call it skin effect. Alternating current with high frequency. Inside, current will become zero, though it is solid, not hollow. Okay, the current will reside on the surface, skin effect. That is why in case of wires, the wires that we use in our domestic purposes, in those wire we have got what? We do not have a single wire, but we have got multiple wires. This is AC. But the wire that we use in our inverter that is works on, that is a battery which is connected. This is DC cell. But in case of battery, we use a wire, but inside you will not be seeing multiple wires. You will see a single wire. If you cut, and you will see a single aluminum wire. But the wire that we connect in our home, that is your that is for use for AC. So that is basically your for AC we use alternating currents. So that alternating current passes through the surface. Okay. I want to show an example actually. Okay, you can see this is wire. This is the wire basically we use at home, right? So many small wires. Okay, why they used to do it? They used to do it in order to increase the surface area, because alternating current resides only on the surface. When you divide a bigger wire into small wires, what will increase? The surface area will increase. Clear? So that is why for using alternating current, they use this kind of wires. Clear? So here current density will become, current density we want, current divided by cross-sectional area. What is the current? I. What is the current? I. What is the cross-sectional area? It is passing through this cross-section. Cross-section is what? Breadth into height. So B into H. This is current density. Let me take another example. A very simple example. Let me take another example. Some very crucial important points I'll tell you. If we use a conductor having non-uniform cross-sectional area, okay, and to make the problem simple, let me call from here to here, the cross-sectional area is increasing uniformly. Now this is connected to a battery of V volt. It is connected to a battery of suppose V volt. And current in the circuit is what? How much? I. How much current is flowing? I. This particular region radius is R, and this particular region radius is what? Thrice. For example, use a radius. Okay, no problem, small r. Thrice r. Okay. So here you have to find number 1, maximum and minimum current density. Find maximum and minimum current density. Suppose from here to here length is your L. Number 2, find J at a midpoint. Okay, along its length. Somewhere in the middle we have to find current density. Now this particular problem I have discussed earlier also. Current is going to be uniform. Okay, it's not like that current here will become bigger, there will become smaller, or it's not like this is bigger, current will grow bigger. No. Okay, through the conductor current is going to be uniform. So since current is uniform, we have the definition of current density. What is that? Current divided by area. So we can see very clearly from here, for constant current density is inversely proportional to the cross-sectional area. Okay, so here cross-sectional area is minimum, so here current density is going to be maximum, and here cross-sectional area is maximum, so your current density is going to be the minimum. Find maximum and minimum. So J maximum, where it becomes J maximum? At the point A. Where it will become maximum? At A. How much will it become? Current divided by cross-sectional area. What is the cross-sectional area? Pi r square. And what will become J minimum? J minimum, where it is? At B. Let me call this particular point as B. How much is current? Current is I. Area will become how much? Pi 3 r square. That is 9 r square. This is minimum current density. This is maximum. This is minimum current density. Second point, find J at a midpoint along its length. At a midpoint. Let me consider. At a midpoint, what will be the cross-sectional area exactly at the middle point? See here, radius is r and the radius is what? Thrice r. So exactly at the middle, radius will become in between r and 3r. So what is the average of what is the midpoint between r and 3r? We can do it like this: r plus 3r divided by 2. How much will become? Okay, don't you think this will become twice r? Is it correct? R twice r 3r. So exactly midpoint. Okay, I'm showing a shortcut actually. Exactly the midpoint, radius will become twice r, because this is increasing uniformly. Okay, so in this situation we can get the radius. So exactly at the midpoint, radius will become twice r. See, when something is increasing uniformly, the mid value is the mid value. For example, from here to here something is increasing. Suppose here it is, let me call from here to there. Okay, this is r, this is r. So from here to here this is increasing uniformly. From 0, how much will become? Twice r. If I call this is r, then from here to here this will become r. So on the upper part, how much will remain? Twice r. Clear? So this is 0, then this is twice r. This is 0, this is twice r. This is increasing uniformly. So exactly at the middle point, how much will become? R. So exactly at the middle point, how much will become? Exactly at the middle point, how much will become? This will become r. Again, from here to here, this is r. So from here to here, this will become total twice r. Anyway, so radius at the midpoint will become twice r. So how much will be the current density at the point C? Let me call this point as C. C will become how much? Current divided by area. Pi twice r whole square. That is 4 r square. This is how we can find current density. So this current density is slowly becoming, okay, this is important from ZEE point of view also, right? If you want to see something more in detail, you can refer to my channel. You'll be getting some more videos related to this on typical problems. So there is drift speed now. Next point is what? Drift speed. Drift speed. And suppose drift speed and mobility. Drift speed and mobility. Let us understand. So for that, let us consider a metal. We understand that inside metal electrons are there. Okay, what sort of electrons are there? Electrons free from bonding. Free electrons are there. These electrons used to have random motion within the metal, like the way you talk about the random motion of gas particles. In kinetic theory of gases, we have talked about that. We have learned about that. So a electron inside will be taking a zigzag path. It will keep on going in different directions. Okay, starting from here, it will go like this, suppose, going like this, going like this, like this, like this. Again, after some time, you know, it may return back to the same point. But as a whole, if you see, it is within it. So it's displacement. Okay, average displacement, you can consider it to be 0. It is not getting displaced in any direction. Finally, you know, it can be considered like this. So average velocity of the electron, okay, we can assume it to be equal to 0. Electrons will go, there will be collision, again it will go, there will be collision, this also there will be collision, that also there will be collision, again it will come here, there will be collision, this collision. Okay, so electrons collide with whom? With the other electrons. With the positive ions it will collide. Okay, so basically these particular electrons keep on moving inside because of its thermal energy. What energy? Thermal energy. Okay, you need to know that when you heat up a material, the ions also start vibrating because of thermal energy. Ion also starts getting, okay, vibrating. When the ions will get vibrated, collisions with the electrons will become more frequent. Okay, so you can understand something like a heavily crowded street. For example, during puja time, the markets and all, it gets heavily crowded during the time of Eid, right? And then when you walk on the street, it becomes very difficult to walk. Or if there is a procession going on and he wants to walk along it, clear? So you understand how you have to walk, so crowded. So it also something like electron also, it happens like this moving again collision, again moving again collision, right? So there is a zigzag part. So in this case, there is no final drift. Final drift का मतलब किसी एक particular direction में इसका displacement we cannot consider at any time. We have to assume the average displacement to be equal to, total displacement will be equal to 0. But to the same material, if you apply an external electric field in these directions, क्या होगा जब electric field apply करोगे? Electrons being negative will experience a force in a direction opposite to the direction of electric field. So electrons will start experiencing a force like this. So it will try to accelerate, but there will be a collision again. Right? You want to run, you'll collide with someone. Again you'll fall, again you will stand up, again you will run, collide with someone, you will fall, your velocity will come to 0. Right? So electrons will accelerate, collide with the ions. Okay? We can assume it will come to rest. Again it will accelerate in the direction of electric field. Again it will collide, again it will come to rest. Okay? So the time between one collision then to next collision, time between two successive collision, एक बार collide हो गया उसका बाद next collision तक, इस time को बोला जाएगा relaxation time, मतलब ये relax है. Okay? और इस path को बोला जाएगा free path. क्या बोला जाएगा? Okay? For example, there one collision, here another collision. This particular path will be called as free path, like the way we have discussed in gases, free path. And this time will be called as what? Relaxed time, relaxation time. Okay? So you see, it's not necessarily that it will keep on, the collisions will occur at a regular interval of time. It is not necessary that it will occur at regular interval of time. Instead, we can call the collisions will take place at irregular intervals of time, random intervals. This is suppose T1, next collision will be after time t2, next can be after t3, okay, next can be after t4, another can be t5, okay, next can be t6, t7, something like that. Okay, so from here we'll get mean relaxation time. Okay, so but anyway there will be a constant force acting on the electrons. So electrons, though there will be collision, but still there will be a resultant displacement in a direction opposite to the direction of electric field. Okay, it will always keep on experiencing a force like this. Okay, so for example, collision, something like that, something, at least it is getting drifted, we'll call drifted in a direction opposite to the direction of electric field. So the average velocity with which the electrons will start moving in a direction opposite to the applied electric field, that velocity will be calling as what? Drift velocity. Okay, so how much is the force on electron? Force on electron is charge on electron multiplied by the electric field. This is the force on electron. So what is the acceleration? Then acceleration will become force divided by mass of electron. This will represent mass of electron. Okay, so we will assume that after collision it will come to rest. So u can be 0. Then what will be the velocity? If we use this equation, v is equal to u plus at, let me use these equations. Then v, we can use the initial velocity to be 0. That means, for example, I have given the example, you are running in a crowded place, you have hit someone, you have fallen down, you have come to rest, again you stand up, again you will start running, again you will collide, again you will fall. If you visualize a situation like that, so the initial velocity will become 0, again it will accelerate. Okay, so this velocity will become 0. What is the acceleration? This is the acceleration of the electron multiplied by time. Time will be called as what? Relaxation time. Okay, we'll consider the mean relaxation time. Time between two collisions, it will accelerate. Okay, so this will be the expression of drift velocity. This will be the expression of drift velocity. This will be the expression of drift velocity. Let me regarding this expression, there is some controversy. Instead of using this equation v is equal to u plus at, we can use this equation also, s is equal to ut plus half at squared. Okay, this appears to be more convincing. I'll get you different expression of drift velocity. Achha, if you express it in the vector form, how much it becomes? Wait a minute. V d bar will become how much? Minus e tau by m e bar minus y, because direction of velocity and direction of electric field is opposite. Electric field towards right, then electrons will move towards left. Achha, if we use this equation, what will happen? We have assumed u to be 0, u 0. Then how much will be the displacement? Half. Acceleration is how much? E by m into tau square. Time we have taken as tau square. Then if this is the displacement in a time of t, then what will be the average velocity? Average velocity should be displacement divided by time taken. So how much it becomes equal to? If you divide by 1 tau, if you bring it here, how much will get? E capital E tau divided by twice m. Here is E by m tau, here it is E by twice m tau. So this particular expression of drift velocity you will get to see in many standard books. But you know, this is the expression given in NCERT. You check it. Okay, this is the expression given in NCERT. So though it appears to be this one, actually this expression of drift velocity will be considering it to be correct. Two reasons is there. Number one, exactly with some limitations, since we are just in class 12, with some limitations, we will not able to understand how this is this one. Okay, properly. It will not be in a, we are not in a situation to explain you all these conditions. Okay, but actually this is, since the expression is given in NCERT, and as far as your 11 and 12 syllabus is concerned, what is given in NCERT, that will be assumed to be correct from exam point of view. Okay, so though it appears to be more convincing, okay, So according to many authors, this is wrong. The actual correct answer is this one. Okay, actual correct answer is this one. So to avoid controversy, you use these particular expressions of drift velocity, okay, which is also being supported by many good authors, right? So that is why this controversy keeps on coming every time. So let me highlight you here only, right? So since this is given in NCERT, you will assume it to be correct, and actually this is only correct expression. So this is, we have seen about drift velocity. Another term was there, mobility, is represented by mu, mobility. What is mobility? Drift velocity per unit applied electric field. Okay, you have applied in electric field of suppose 10 volt per meter. Okay, and the electron has gained average velocity of, how much is that? 20, for example. Actually drift velocity is very small. This is for an example I am taking. 20 meter per second. Then how much will become mobility? Mobility is what? Drift velocity per unit applied electric field. How much is that? 20 divided by 10, that is 2. Okay, unit you can calculate by yourself. So under unit applied electric field, how much drift velocity the electrons will be gaining? That will be called as what? Mobility. Okay, mobility. Drift velocity per unit applied electric field. So what is the unit of it? What is the dimension of it? You can find it from there. What is the dimension of it? You can find it from there. You do that by yourself. Dimensional formula of mu. This is velocity, LT minus 1. This is electric field. Electric field, how can you take? Newton per coulomb. Newton per coulomb. Coulomb you replace by current into time. You'll get it. Okay, this is mobility. Drift velocity. Actually the drift velocity is how much? Drift velocity is approximately 10 to the power minus 4 meter per second. Again, in some books you may find it 10 to the minus 3, 10 to the minus 3. Okay, so 10 to the minus 3 also you may find. I'm picking up 10 to the minus 4. Drift velocity is approximately, and this velocity is too small in comparison to thermal velocity of the electron. You know, thermal velocity of the electron is approximately 10 to the power. Thermal velocity. Thermal velocity means when there is no electric field. When there is no electric field, electrons are moving. One collision, next collision. In between these two collision, velocity. Okay, that velocity is approximately 10 to the power 5. In some books 10 to the power 5. In some books 10 to the power 6. Okay. So that is thermal velocity of electrons is 10 to the power 6 meter per second. Okay. According to some books it is 10 to the power 5. So both values are there. So I am giving you both the values, right? So there should not be huge difference, 10 to the power 5 and 10 to the power 6 of the order, right? This is not equal. This is of the order. So you have seen this, what to say, your drift velocity, the velocity gained by the electron, okay, under the action of an electric field. Okay, this is actually is too small in comparison to its thermal velocity. Okay, and this is thermal velocity at room temperature. Room temperature. This is thermal velocity at room temperature. Now, from drift velocity, let us see drift velocity and current, the relation between drift velocity and electric current. Okay, in order to understand it, we will consider a portion of a conductor. You try to understand it. This is a conductor. Here let me consider a small portion of this conductor. Like this, a portion of the conductor let me consider. Okay, and let me say the electrons are moving along these directions, in that direction. Suppose the electric field is towards left, electrons are going towards right. And suppose from here to here the electrons takes how much time? T second. Electron takes how much time? Suppose from here to here it takes delta t second. Delta t. Under the action of electric field. Electric field is like this. What velocity? With what velocity electrons will move? Drift velocity. So from here to here, this particular distance, if I call it as delta x, then delta x will become how much? V velocity into time, distance. So from here to here, the electron takes how much time? Delta t. So the distance travel will become velocity into time, that is delta x. Now, same cross section, let me consider here and show you something. मैंने उसी क्रॉस सेक्शन को यहां पर भी कंसीडर कर लिया. ये जो पार्टिकुलर एलिमेंट है इसका वॉल्यूम देखते हैं. ये हो गया इसका लेंथ, ये हो गया इसका एरिया ए. सो कितना होगा वॉल्यूम? इसका वॉल्यूम हो जाएगा तुम्हारा ए इंटू डेल्टा ए इंटू डेल्टा एक्स वॉल्यूम. इस वॉल्यूम के अंदर कितना इलेक्ट्रॉन्स है? हाउ मेनी इलेक्ट्रॉन्स आर देयर? फॉर दैट we'll first consider a number, small n. इसको कहते हैं number density of free electrons. Number density of free electron. Number density of free electron means number of electron per unit volume. Okay? If suppose in this volume total number of electron is n and total volume is v, then small n is what? N divided by V. So obviously what will be the total number of electrons? N into volume. So in this particular region, total number of electrons, if I call it as capital N, what will happen? This will become small n into volume. What is volume? A into delta x. Now charge on each electron is E, small e. Okay, so what is the total charge on the free electrons present in this particular volume? Total charge present on the electrons, okay, is what? Number of electron multiplied by charge on each electron. So we'll get it as what? E into N A delta x. Okay, so this is the total charge which is within this particular region. And all the charges are moving towards right. Okay, we're considering the charges to be moving towards right. So how do you visualize? If I consider through this particular cross section, if someone asks me through this particular cross section in a time of delta t, how much charge crosses, then I'll call the charge crossing this particular cross section in a time delta t is nothing but delta q, because all the charges are going towards right. Let me show you like this. All the charges are going towards right. Clear? Okay. The electrons, so many electrons are there. Let me show you a dotted line. थोड़ा हिम्मत रखो, समझ में आ जाएगा. All are going towards right. All are going towards right. This is a cross section. This cross section is this one. Okay. So the last electrons, those which were here, from here to here, how much time they takes? It takes a time of delta t. Means when these electrons will reach here, जब ये इलेक्ट्रॉन जाके यहाँ पहुंचेगा, तब तक इसके सामने जितना इलेक्ट्रॉन्स था सब निकल चुका होगा. Okay, the time in which this will go and reach there, in that particular time इसके सामने जितना इलेक्ट्रॉन्स था सब इलेक्ट्रॉन निकाल गया. मतलब कितना इलेक्ट्रॉन निकाल गया? इतना इलेक्ट्रॉन निकाल गया. इतना इलेक्ट्रॉन का चार्ज कितना है? डेल्टा क्यू. दैट मींस इतना इलेक्ट्रॉन ये पार्ट इस पार्टिकुलर क्रॉस सेक्शन से पेनेट्रेट किया इन हाउ मच टाइम? इन अ टाइम ऑफ delta t. So that is why here the current will be defined as delta q divided by delta t. What is delta q? The total charge on this particular portion which will cross this cross section in a time of delta t. Okay, because when it will go and reach there, this will come and reach here. Okay, ये आगे वाला, ये पीछे वाला. What is delta q? NE A delta x divided by delta t. What is delta x by delta t is nothing but delta x by delta t is nothing but velocity. What velocity? Drift velocity. So I is how much? NEA V. These are important relations. The relation between current and drift velocity. There is a relation between current and drift velocity. Try to understand. Okay, so from here we can define current densities also. You bring area here, current divided by area. How much will become? NEVD. Okay, this is scalar, but these two are vectors. If I put J bar, then it will become minus NEVD, because direction of drift velocity and direction of current. This is the direction of current, they are opposite. So this is current density, relation between current density and drift velocity, relation between current and drift velocity. Okay, this is the vector form showing the relation between current density and drift velocity. See here, I'm trying to go as slow as possible so that you understand. Okay, kindly let me know your difficulties in the comment section. Okay, comment karna mat bholna. Okay, or do like the videos, pass your comments, share it, right? So VD drift velocity is nothing but I divided by NEA. Okay, so if you think the current passing through a conductor, if it is constant, basically it uses to be constant. Okay, current passing through a conductor is constant, and you see drift velocity is inversely proportional to what? Area. Clear? Drift velocity is inversely proportional to area. Okay, so let me tell you a very crucial point now. This particular conductor, I was connecting a battery here, right? V volt. Current was how much? I. If I consider two dotted lines, line 1 and line 2. Okay, tell me in which part your drift velocity will be more, in part 1 or in part 2? In which part drift velocity will become more? So obviously A1 is less than A2. This area is small, this area is bigger, larger. So drift velocity is inversely, this is smaller, drift velocity will become bigger, V1 greater than V2. Okay, so if I ask you where current density is more, current density will follow the same ratio. Current density is nothing but current divided by area. So in 1, current density will become greater than the current density in 2. Now if I ask you, if the electric field in 1 is E1 and in 2 it is E2, which electric field will become bigger? This one I am leaving for your homework. You let me know in the comment section. Okay, you tell me where electric field will become more, here or here, or within the conductor you will have a uniform electric field. Think about that, right? Through the conductor, whether you will have a uniform electric field or you will have different electric field. If you have different electric field, then which electric field is going to be bigger? Very simple. The solution you already have in my lectures. You will get it. Okay. So what are relations we have got? Drift velocity, how much we have got? Relations we have got between, one is drift velocity we have got, how much is that? E capital E by mass into tau, this was one relation. After that what we have got? I is equal to NEA VD, फिर क्या मिला? J is equal to NEVD. Anything else we have got? We have got, from here we will get a relation. Okay, J, you see another important relation is coming. What is VD from here, from the first equation? What is VD? E capital E by M into tau. Oh, we have got relations here. And E square tau divided by M into E. So we have got a relation involving some fundamental vectors of electrodynamics. JIPMER. the elementary vector of electrodynamics. This is electric field, another vector. Okay, so if I put J bar, this will become E bar, both in the same directions. Okay, J bar is opposite to the direction of electron, and E bar is also opposite to the direction of motion of electron. So here this particular part is basically can be represented by a term J is equal to, this is called sigma into E. What is this sigma? The sigma is called conductivity. Remember this relation, huh? The sigma is called what? Conductivity. Conductivity is a property of a conductor. Conductivity, resistivity, conductance, resistance. Remember something? Class 10. Okay. कुछ तो पढ़ के आए हो क्लास 10 में, है क्या नहीं? हाँ. Good. Conductivity. In one way, this is called Ohm's law in vector form. This is what law? Ohm's law. We'll be discussing Ohm's law very soon now. Ohm's law in vector form, or they call Ohm's law in microscopic view. Microscopic view. This is Ohm's microscopic view of Ohm's law. Because when you say Ohm's law, we understand something V is equal to IR, right? Actually, V is equal to IR is not Ohm's law. There is a relation we get from Ohm's law. Okay, so this is another form of Ohm's law. Okay, so let me come to it. What is Ohm's law? I'll show you in another way. By Ohm's law, we understand in a simplest manner. Let us consider a conductor, and this conductor, suppose we are connecting to a battery of V volt. Clear? This conductor that we are using, if we assume it's some physical parameters to be constant, for example, the length should not change, length should be constant, cross-sectional area, something like density, something like temperature. So these some physical parameters, if it does not change, then how much current that will pass through this conductor will depend on what is the potential difference applied across it. If you apply more potential, the current will become more. If we apply less potential difference, current will become smaller. Clear? But condition is what? Okay, some physical parameters like temperature, length should not change. Then what will happen? The current passing through the conductor will be directly proportional to the potential difference applied across it. So from here we get the relations. Okay, I is equal to, once we make it equal, okay, a constant of proportionality comes 1 by R. We can call it as Z, capital Z. This is what? Capital Z. What is this? Conductance. What is R? Resistance. Okay, ये class 10 में पढ़ के आए हो. It's not something new for you. So we have got an expressions here. V is equal to R I. इसको हम कहते हैं Ohm's law. Actually Ohm's law ये है. This is a relation we get from Ohm's law. But here to this particular expression to represent it Ohm's law, याद रखना